my lab has two major focuses. One is a photochemical project. We're effectively, in the long term, trying to design molecules that you can use to release a drug using light. So that's kind of an interesting idea because humans are not jellyfish, so it's not a really intuitive concept. But the idea is that you could, systemically deliver a drug that is inactivated by some sort of capping molecule that's light sensitive, and then you could activate it right at the site of the disease by irradiating it with light. So if you've ever done the experiment where you take a flashlight and put it up to your hand or in your mouth or something, and you see that it's the red wavelengths that come through, it turns out that those wavelengths of light actually do penetrate into tissue pretty far. And if you go a little bit farther than the red and into the near infrared, it actually penetrates even further. So what we're trying to do is develop these photochemically sensitive capping molecules that when you irradiate them with near IR light or red light, that they'll actually be able to release a cargo, a drug, and be able to use that to activate it right at the site of disease. So for example, the classic one is in chemotherapy, where you deliver these systemic poisons basically that kill healthy cells and cancer cells, and hopefully they have selectivity. But all the terrible side effects that you get from chemotherapy are from it also killing the healthy cells. So if you could mask the toxic drug into an inert form, deliver it systemically, and then activate it only at the site of the tumor, then hopefully you could eliminate some of those side effects. So the way we would do that is by irradiating it with light. And the other project is more related to material science. And so there we're trying to make stimuli responsive plastics and polymers that can change their properties dynamically in response to environmental cues or stimuli. So we're used to normal plastics, like you go to Walmart, everything's wrapped in plastic, and most things are made of synthetic polymers these days, but they always have one set of properties all the time. So what we're trying to do is develop dynamically responsive polymers and plastics that can change their properties as the environmental conditions change. So they could change their properties on a change in temperature or pH or light level. And so you could imagine developing like dynamic fabrics or chemical sensors, something that where you would get a change in the property of the polymer in response to stimuli. And so the way we're doing that is by using organic free radicals and using a change in the spin state of the radical to effect a huge change in the property of the material based on very mild chemical stimuli that you might get in normal life. So we have two major projects, one the photochemical project, one that's in material science, but they kind of bridge all of these different fields of organic synthesis and computation and photochemistry, and working with radicals is its own set of challenges. So we do a lot of EPR spectroscopy and things like that. And so it kind of merges a lot of different fields, and it touches on material science and biology and medicine as well. I guess the phrase work-life balance kind of goes back to the days when especially organic chemistry was guilty of this, that people kind of were consumed entirely by their research, and they made no time outside of their laboratory research to have friends and have hobbies and pursuits outside of chemistry, and that was never took a vacation, and that was like a highly unhealthy situation. And I would say organic chemistry is probably particularly guilty of this. But the things are changing a lot now, and I think people have a greater appreciation that that's an unhealthy way to live life. And so I view work-life balance as, you have to take vacations, you have to take time when you're focusing on other things, you have to make time in your life for your friends and family and hobbies, things like that. Everyone who joins my group has to take vacation, basically. At the same time, I question the idea of work-life balance, just because when I come to work, I don't think of it as like putting my life on hold. I think of it as just a different part of my life. So when I come here, I'm excited to come to work every day. I love what I do. I love working with the people in the department. So I don't feel like I'm putting my life on hold when I come into the office and work with students. We do a lot of different things. So we do, the main rate limiting step in our lab is organic synthesis. So we're making molecules the universe has never seen before. And that always presents challenges. So that's often the slow step and what people end up spending most of their time on. But then at the end of the day, we're interested in what these molecules can actually do. So on the photochemistry side, you'll learn a lot about photochemistry and photophysics. And we're also trying to understand the rules of how photochemical reactions work. And so that's a really difficult problem because all of your chemical intuition that you've developed based on thermal reactions that you learned maybe in sophomore organic chemistry, you can pretty much throw those all out the window for photochemical reactions because all the rules are totally different. And so we're trying to also learn those rules on the fly so that we can help develop these photochemical light-sensitive molecules. We do a lot of laser flash photolysis, which is basically where you can excite your molecule with a very, very short pulse of laser light and then follow all the reactive intermediates over time. And that allows you to map out the entire photochemical mechanism and how it works. So we get experience with laser spectroscopy. We do a lot of computation. So most of my research group members, when they join the group, are terrified of doing computation because the reason they're usually organic chemists is because they didn't like PChem as much. But it turns out it's not as hard as it seems, and most people in the group end up doing some computational analysis as well that helps us design the molecules and interpret the surprising findings that we had, and it really helps to accelerate our research project by having those things. So students that graduate from my lab have a pretty broad skill set in organic chemistry, photochemistry, and materials science. Guess I would be considered more on the hands-off style in the sense that I'm not sitting behind someone while they're shaking a SEP funnel. I don't dictate what hours students have to be in the lab. At the same time, I also have an open office policy where people can come by anytime and ask me questions, and that's kind of like my favorite part of the day is when students come with me with results and we can talk about like the next steps and what the interpretation of that is. So what I like to do is to make sure that students are really well trained when they first join the lab, and then take the training wheels off and they can kind of go at their own pace and, you know, have a certain freedom to work when they want, how they want, and develop their own style. We do a lot of collaborations actually, both in the department and at different universities and even in different countries. So we have a long-standing collaboration with Emily Smith, who's an analytical chemist in the department, and she develops microscopes for being able to look into cells with really, really good spatial resolution. So we've collaborated a lot with her on the photochemistry project. So we've been able to test a lot of our molecules in cells, and she's tested to make sure that they have no problems like toxicity and things like that. And that's been a really wonderful collaboration because, you know, no lab can do everything, especially if it's an interdisciplinary lab. We've had collaborations on the, you know, more of the physical chemistry side with David Phillips at Hong Kong to do ultra-fast laser spectroscopy. We've had probably half a dozen collaborations with people at different labs around the world looking at how photocages can be used in particular biological contexts and being able to use them in photomedicine. So my lab does not work with cells or with mice or any of that, so we collaborate on that aspect of the project. Best part of being at ISU, I would say, is the people. So I think that one thing that makes Iowa State really special is that the people here are really wonderful. You have that Midwest nice, you know, the faculty are all really great, really collegial. It makes collaborating within the department really easy. I would say that our facilities managers and the people that work and man the instruments are really top-notch and wonderful, make life so much easier, and they're constantly looking for ways to improve everything. The grad students here are fantastic. They're often awesome to work with. It's been a real pleasure. I think that you can duplicate a facility, you can duplicate an instrument setup. What is hard to duplicate is to get the wonderful people together, and I think that's what makes Iowa State special.